Integration. I'm going to start looking at integration by trying to solve a problem, and that problem is, how do we find the area underneath a curve? We have formulas for certain shapes which are nice and easy: rectangles, triangles, circles, trapezium, rhombus, all sorts of shapes we have formulas for, but there's a heck of a lot of shapes we don't have formulas for. Something like this: if I wanted to find the area underneath this curve, the best I can really do is estimate it with ones that I do know formulas for. I've picked the rectangle here. If I was to draw in a couple of rectangles, what I do know is that the area underneath that will be less than. But it'll give me an estimate. How good is the estimate? Yeah, let's see. The area of these two rectangles added together would be, well, I've made the width of each one 1. So I'm finding the area from going from x equals 0 to x equals 2. I've split it into two rectangles. So the width of each rectangle is 1. The height would be whatever the function value is, so function 1 plus function 2. So what I do know is the area under this curve would be less than 9. Theoretically equal to, but obviously not equal to when we look at this particular shape. But I could have drawn a different set of rectangles. I could have drawn these blue ones. Now, okay, the first rectangle here isn't really a rectangle, it's just a straight line, because its height would be 0, and the second one would have a height of function 1, which is 1 cubed. But I know the area I'm trying to find would be bigger than that. So what I do know is this area I'm trying to find is in between 1 and 9. So it kind of makes sense to, well, maybe if I average those two, I'd come up with an estimate. The estimate is 5. Now, it turns out that the actual area is 4. It's not a great estimate. So how do I improve it? Well, if I change the width of those rectangles, I'll make them smaller. Because if I get more rectangles, that overestimate is going to be less than the one I did before, because I've cut out a bit. These, what we call outer rectangles, the ones that give us an overestimate, would then have an area of 5.76. And if I was to draw the, what we call the inner rectangles, the one that gives us the underestimate, that would give us an area of 2.56. If I was to average those, it's a bit better. Remember, we said the exact amount was 4.16. What if I made those rectangles even smaller? So now I've broken it up into 10 rectangles. Each one of those would have a width of 0.2. 4.84 for the outer ones now, or the overestimate. And the inner rectangles, if I draw those ones in, we get an estimate there of 3.24. Average those, I'm now getting very close, 4.04. So what's happening? As I shrink those rectangles down, the overestimate is becoming smaller and smaller, as is the underestimate. So ideally, what I want to do is to make that width as small as possible. Alright, let's have a look just to some random function here, y equals function x. But what we're saying is, as those widths decrease, then we know our estimate's going to become more and more accurate. I'm going to create a new function, call it the area function. And I'm going to define it as the area from 0 up into whatever the x value happens to be. So area C would be the area going from 0 to C. Area x would be the one going from 0 to x. Now I could estimate it with any shape I like. Let's say I estimate it with a rectangle. So the width of that rectangle would be whatever x was minus whatever c was. And then the height would be the function value of x or the function value of c, depending on whether I'm talking about an underestimate or an overestimate. I've gone with function x for this one. It's an approximation, but area x minus area c would be approximately equal to the area of this rectangle. Remember this area function. It'd be great if I had a formula for the area function. If I rearrange that and make function x, because that's the thing I know the equation of the curve, I know what function x is, it would be approximately equal to this area function when I substitute x in minus, when I substitute c in over x minus c, the width of that rectangle. Well, rather than writing the width of the rectangle as x minus c, let's just call it h. You might be thinking, why didn't you call it w? Well, there's a good reason why I didn't. If I change that to h, I could now say this is the area function when I substitute in whatever c was plus the width of the rectangle minus area C. And that looks very familiar. What we say, as the width of the rectangle decreases, so as that h gets smaller and smaller, the estimate becomes more and more accurate. In other words, as h approaches 0, as that width gets smaller and smaller and smaller, that area is going to become exact. And we can play around with that idea of limits we looked at before. We say, well, what's the limit of this thing as it approaches 0? Because that would be the exact amount. Now, I'm interested then in what is the limit of this. So function x, the thing we know, is equal to the limit as h approaches 0 of area, this area function I want to find, c plus h minus area c over h. And that is our first principles formula for differentiation. I can easily now change x and c. So remember, we're saying h is approaching 0. Well, if h is approaching 0, then x and c are approaching being the same thing. So if I now swap in x for c, I can now say this, that the function that I know is actually the derivative of this area function that I want to find. And now we can do it. So the area under our curve, y equals function x, if I want to go between two values, a and b, here's the notation that we'll end up using. So our area function, or the actual area, our area will equal, now this symbol here, it's an S, by the way, that's the letter S. It's a very old way of writing the letter S, but that's what it is. It's what's called the long S. If you look at very old texts and books written, I'm talking hundreds of years ago, you'll see it there. People mistakenly look at it now and think it's an F, but it's actually the long S. What will it equal? Well, it'll equal some function that I can find, and what we do is we'll substitute in the top one minus the bottom one, and that will give us our area. Well, that function that we want to find is what we were looking at the other day. It's the primitive function. So how do we go back from the derivative to the original function? So actually that area function that I'm trying to find is the primitive function of the equation of the curve itself. So here's the question we were trying to do. And here's how we get the exact amount that I knew it was going to be. So y equals x cubed. I want to find the integral going from 0 to 2 of x cubed. We've got to find the primitive function, which is add 1 to the power over the power. Now when I go to the next step, it goes to square brackets. Notice the limits go to the right hand side. For some reason we tend to put it there, but I'm going from 0 to 2. Substitute the top one in, 2 to the power of 4, the bottom one in, 0 to the power of 4, and we get our answer, our exact amount of 4 units squared. Let's have a look at this one then. So if I now wanted to find the integral going from x squared plus 1, add 1 to the power over the power, so I'll find the primitive, substitute in 3 minus substitute in 2, we get our answer. And you'll notice there's a subtle difference in my answers here. The first example, I wrote units squared because we were finding an area. The second one, it's just a value. Nowhere in that question did it say, find the area under x squared plus 1. It simply is, hey, find this integral. In that case, it's just a number. No, I don't put units on it. Okay, let's do this one. X to the power of minus 3. This is the one where we have to be careful because negative numbers, oh hang on, I'm adding to the negative. So add 1 to the power is actually negative 2 over that power of negative 2. Substitute in. You'll notice I took it out of index form because I knew I was dealing with fractions, so I find that easier to substitute into. 9 over 800. Here's an interesting one. We have to find the derivative of this integral. Remember, another notation for differentiation is d dx of some function that we're trying to find the derivative of. Well, what we're trying to find the derivative of is actually this integral. Okay, well what happens here? Well, let's work out this integral first so we know what we're trying to differentiate. So I'm trying to find, I would integrate it and come up with some primitive function, I've called it capital F. Substitute in x, substitute in c. I'm finding the derivative of function x minus function c. Well, hang on, what is the derivative of function x? Well, now I'm going back, it must have been function x minus, now when I substitute the constant into the function, I'll just get a constant number. And when I differentiate a constant number, I get 0. So in fact we get this nice little formula here that what is it saying? All it's really saying is differentiate the integral. They're inverse operations. So they've cancelled each other out. If it is a one here where I'm substituting numbers in, the x is unknown, so it stays, the constant one becomes 0. So we'll just get whatever function x is. We just replace t with x basically. Okay, there's a little start on this journey into integrate.